Hello and greetings to all who are watching this video. Well, let me introduce myself. My name is Dr.R.M.Joany, working as an associate professor in the Department of Electronics and Communication Engineering at Sathyabama Institute of Science and Technology, deemed to be University, Chennai. In this video lecture, I am going to discuss about the design and implementation of a synchronous counter, which is one of the important topics in the course Digital Logic Circuits for the program BE Electronics and Communication Engineering. Now let's get started with the topics. Before getting into the design and implementation of a synchronous counter, let us try to understand what is a counter. So a counter is a sequential circuit, and in digital logic and computing, a counter is known as a device that is used to store or count the number of process or the event that has occurred, and often it is counted with respect to a digital clock. And flip-flops are the basic building blocks of these counters. So in digital logic, it is actually used for counting the pulses, and it is one of the widest applications of the flip-flops, and it is actually designed with the help of the flip-flops connected in a cascaded fashion and applying digital clock to it. That is about the simple information of counter. Now let us try to understand, or let's have a glimpse of the various counters that is available in the market. That is, this is a mechanical counter, and this is some of the examples of the digital electronic counter. So these counters are designed with the help of the combination of the flip-flops connected in a cascaded fashion, and these are widely used component in the digital circuits. Most often these are manufactured with the integrated circuits, or it could be integrated as a part of a larger integrated circuits. So this is how the counters are playing a major role in various applications. Now let us try to understand what are the various applications of the counters in a real-time life scenario. So for example, we would have seen a counters in a bank token. That is, when we go to the bank, we come across the tokens, bank tokens. So bank token counters at the cashier section is one of the most important applications of a counters, and the counting system of a automated product line in the manufacturing industries, as well as the digital clocks, as well as the digital stopwatches, and even in the smart watches, and the timers that is required for turning off of the power supply in the automated water supply system, as well as some of the sensor control counters. These are the various applications of counters. Then next, let's get started with the synchronous counter design. So before that, let us try to understand what is a synchronous counter. So synchronous counters are counters that are triggered simultaneously by a single clock pulse. That is, a single clock is applied to all the flip-flops. As discussed earlier, the synchronous counters are designed with the help of connecting the flip-flops in a cascaded fashion, and a single clock is supplied to all the flip-flops. And here the number of flip-flops determines the count limit of the number of states the counter is going to have. For example, the number of states the counter is going to have is decided by the 2 to the power of number of flip-flops. That is the design of the synchronous counter. So the number of states used here is called to be the modulus. For example, if it is a modulo 12 counter, it would be counting from 0 to 11. That is, it is a 4-bit. That is, 4 flip-flops are used: 0, 0, 0, 0 to 0, 1, 0, 1, 1, and it would require 4 flip-flops. Therefore, 2 to the power of 4 is equal to 16 states. Therefore, 12 out of 16 states, 12 are being used to count the sequences. So it is an example of a modulo 12 counter. Similarly, we can define a many number of synchronous counters. Now, let's get started with the design of a synchronous counter. So what are the steps involved in the design of a synchronous counter? So there are 5 steps in designing the synchronous counter. As a step 1, we need to decide the number of flip-flops. As we have discussed in the previous slide, the number of flip-flops is decided by the modulo number. Therefore, or the number of states it is going to occupy. Therefore, that should be decided before we start the design of the flip-flops or the counters. And then in step 2, we have to make use of the excitation table for the flip-flop which we have chosen, and then we have to create in the step 3 the circuit excitation table with the help of the state diagram. That is about step 3. In step 4, using the excitation table and with the help of the corner map, we have to obtain the simplified equation or the Boolean expression. So corner map is a widely used mapping system, visual system that is used to simplify the any algebraic expression to a Boolean expression, that is sum of products or products of some form, so that it would be easy to implement any digital circuits with less number of flip-flops. So this is how the corner map simplification is done. So with the help of the excitation table and the simplified equation Boolean expression obtained from the corner map, we will be drawing the logic diagram in the step 5. So that is the end of the design of a synchronous counter. So these are the various steps involved in the design of a synchronous counter. So now let us get started with each step one by one. So step 1. In step 1, we have to decide the number of flip-flops. So here you see the number of flip-flops. So as an example, we are going to consider the design of a modulo 6 synchronous counter. So in step 1, we have to decide the number of flip-flops. So as it is a modulo 6 counter, the number of flip-flops is equal to 3 as it is, that is modulo 6 counter is equal to 2 to the power of n is equal to 6. So with that, we will be defining the number of flip-flops required for designing this counter is 3. And the number of states it is going to count is, that is 6 counter states. And the counting sequence, it is going to be 6, that is it counts from 0 to 5. That is, it is going to be a 3-bit counting sequence, that is from 0, 0, 0 to 1, 0, 1. And the clock pulse is given to all the flip-flops as it is a synchronous counter. And as an example for this modulo 6 synchronous counter, I am going to consider JK flip-flop. That is, we are going to make use of JK flip-flop to design this modulo 6 counter. So now let us get started to the step 2. So before going to the step 2, we should understand what is an excitation table. So this excitation table lists the required number of input combinations that is actually given for every change of state in the counter. For example, the excitation tables are used for designing the flip-flops or counters. So the truth table contains the inputs and output combinations, whereas this excitation table contains the present state, next state, and the possible input combinations for every change of state. So this picture shows the glimpse of the excitation table of all the flip-flops, that is SR flip-flop, JK flip-flop, D flip-flop and T flip-flop. For example, SR flip-flop, Q of T is the present state and Q of T plus 1 is the next state, and S and R are the input combinations. For example, present state is 0 and the next state Q of T plus 1 is 0. The input combinations, it is going to be 0, don't care for SR. Similarly, for present state 0 and the next state 1, it is going to be 1, don't care. So similarly, we have for all the flip-flops, the excitation table. So with the help of this excitation table, we are just going to create the circuit excitation table along with the state diagram in the next step. So in step 2, we need to understand or we need to decide which flip-flop we have chosen, and we have to look into the excitation table of that corresponding flip-flop. Okay, now let us move to the step 3. So in step 3, let's draw the state diagram for the given counting sequence and create the circuit excitation table. And let's have a picture of the excitation table for the JK flip-flop. So JK flip-flop, the present state is represented as Q of t and the next state is represented as Q of t plus 1, and we have the input combinations J, K. And for 0, 0, the input combinations are going to be 0, don't care, and for 0, 1, it is 1, don't care, and for 1, 0, it is going to be don't care 1, and for 1, 1, it is going to be don't care 0. And in the state diagram, the first state it is going to be 0, 0, 0, second state it is going to be 0, 0, 1, and the third state 0, 1, 0, and the fourth state 0, 1, 1, fifth state 1, 0, 0, and the sixth state it is going to be 1, 0, 1, and after the sixth state it again counts to the first one, that is 0, 0, 0. So it keeps counting in a looping sequence. And in the circuit excitation table, the various fields are the present state, next state, and the various input combinations. So the present states and the next states are represented for the 3 flip-flops, that is Q2 of t and Q2 of t plus 1 are the present state and next state of the flip-flop, the JK and J2. And Q1 of t and Q1 of t plus 1 are the present state and the next state of the flip-flop 1, and its outputs are going to be J1 and K1. And Q of t, Q naught of t and Q naught of t plus 1 are the present state and the next state for the counting, that is for the flip-flops, the F00. And now let's get started. First we have to fill all the present states of this column, that is the present state Q2 of t, Q1 of t and Q0 of t. Now let us try to fill. So first state it is going to be 0, 0, 0, and next it is going to be 0, 0, 1, and next it is going to be 0, 1, 1, and next it is going to be 1, 0, 0, and then 1, 0, 1. Okay, so we have filled all the present states. Next step, we have to fill the corresponding next states for the current present state. For example, for 0, 0, 0, the next state it is going to be 0, 0, 1. That is Q2 of t plus 1, Q1 of t plus 1 and Q0 of t plus 1. So 0, 0, 1. And for 0, 0, 1, the next state it is going to be 0, 1, 0. So 0, 1, 0. Similar fashion, we have to fill the next states for all the corresponding presents. So for 1, 0, 0, it is going to be 1, 0, 1, and for 1, 0, 1, it is going to be 0, 0, 0. Again, the first state. So now we have filled all the present states and the corresponding next states. Now, the next step, we have to look at the excitation table of the JK flip-flop and fill the corresponding input combinations for the flip-flops to flip-flop 1 and flip-flop 0. Now let's get started and try to do it. For example, with the help of Q2 of t and Q2 of t plus 1, we have to look into the excitation table and fill J2 and K2. For example, 0, 0, it is going to be 0, don't care. So 0, don't care. And for 0, 0, again it is 0, don't care. And for 0, 0, again it is 0, don't care. Then we have 0, 1. For 0, 1, it is going to be 1, don't care. 1, don't care. Similarly, for 1, 1, it is going to be don't care 0. And for 1, 0, it is going to be don't care 1. Now we have completed the input combinations for the flip-flop 2 for J2 and K2. Next, we will pass on to the next step. So next step, we have to give the input combinations for J1 and K1 using the present state and next state Q1 of t and Q1 of t plus 1. So let us look at the Q1 of t and Q1 of t plus 1 and look at the excitation table. With the help of the excitation table, let us try to fill J1 and K1. So what are the combinations? That is 0, 0, it is going to be 0, don't care. So, and 0, 1, it is going to be 1, don't care. Similarly, for 1, 1, it is going to be don't care 0, and for 1, 0, it is going to be don't care 1, and similarly, we can fill for the other combinations as well. So now we have completed filling the input combinations for the flip-flop 1, J1 and K1 with the help of the present state and next state Q1 of t and Q1 of t plus 1. Next, we will move on to the further step, the last one, the flip-flop 0. The input combinations are J0 and K0 by considering Q0 of t and Q0 of t plus 1. And with the help of the excitation table, in the same fashion, we have to give the input combinations. So, let's get started. For 0, 1, it is going to be 1, don't care. Therefore, 1, don't care. And for 1, 0, it is going to be don't care 1. So, in a similar fashion, let us quickly try to fill J0 and K0 for all the present state and next state combinations. Now we have completed creating the excitation table. Okay, for the present state and next state combinations, what are the possible input combinations for all the 3 flip-flops, flip-flop 0, flip-flop 1 and flip-flop 2. Okay, now let's try to simplify this excitation table with the help of the present state and the input combinations and with the process of corner mapping. So for that, we have to create a 3-bit. So as we are using 3 flip-flops, we need to make use of 3-bit corner map. So this is how it is created, corner map for J2, K2, J1, K1, J0 and K0. Now let us try to write the input present state combination, that is Q2, Q1 and Q0, similarly Q2, Q1 and Q0. And the various inputs, that is present states, are 0, 0, 0, 0, 0, 1, 0, 1, 0 and all other combinations. Now let's get started and try to fill the corner map table. So for 0, 0, 0, the input combinations are going to be J2 and K2. So 0, don't care. So it is 0, don't care, 0. So this is the position of 0, 0, 0. And next one, for let us simultaneously try to fill that position in all the tables of the corner map. For J1, K1, it is going to be 0, don't care, and for J0, K0, it is going to be 1, don't care. So now we have completed filling the corner map position for 0, 0, 0. Similarly, next try to do it for the next case. So the next present state is 0, 0, 1. For 0, 0, 1, where is the position? 0, 0, 1 here. So it is going to be 0 and here it is going to be don't care and here it is going to be 1. So that 1 is placed here. And next one it is going to be don't care, and next this don't care will come here and this one will come here. So now we have completed filling the present state 0, 0, 1. Next we will move on to the further step. Okay, that is for the next present state it is going to be 0, 1, 0. So where is 0, 1, 0? It is going to be here. 0, 1, 0, it is going to be 0 for J2 and it is going to be don't care for K2 and it is going to be don't care for J1 and it is going to be 0 for K1 and it is going to be 1 for J0 and for K0 it is going to be don't care. So now we have completed for the third present state. Next we will move on to the fourth state, fourth present state, that is going to be 0, 1, 1. So 0, 1, 1 is the position here in the table. Therefore, it is going to be 1, don't care. K2 it is going to be don't care. And for J1 it is going to be don't care. and K1 it is going to be 1. Similarly, J0 it is going to be don't care, and K0 it is going to be 1. So now we have completed the fourth state. Now let us move on to the next state. So in a similar fashion, we have to fill the position 1 0 0. So 1 0 0 it is going to be in this position of the corner map. It is going to be don't care, it is going to be 0, and it is going to be 0, and it is going to be 0 again, don't care, and here it is going to be 1, and here it is going to be don't care. So we have completed the fifth state, and the last present state it is going to be 1 0 1. So for this, the various input combinations are here. So there is 1 0 1. This is the position in the K map, and this is the position. So 1 will come here, and then here 0 will come here, and here don't care will come, and here this don't care will come here, and then this one will come here. So now we have completed all the process of filling the K map. So remaining the blank empty K maps could be filled with don't care terms. So we are going to fill the don't care terms. So let us try to fill the don't care terms. So now we have completed filling the corner map. So next step we have to do the mapping process for creating the simplified equation. So we can map 1 and don't care for J2. So what is the position here? J2 it is going to be Q0, Q1, Q0. So it is going to be Q1, Q0. Is it clear? So it is going to be Q1, Q0. Then for K2 it is going to be, you can map all these 4, therefore it is going to be Q0. Okay. Next for J1 you can map here this position, these 2. Therefore this position is going to be Q2 bar Q0. It is going to be Q2 bar Q0. Q2 is 0 0, and here it is going to be Q0. Therefore it is going to be Q2 bar Q0. Okay. Then for K1 we can map all the 4. Therefore it is going to be Q0. Next J0. So next J0 we could combine all the terms because we have only ones and don't cares. Therefore it is going to be 1. In a similar way, K0 we can map all the terms here. Therefore K0 again it is equal to 1. Now we have completed the simplification process using the corner map. So in step 3 we have created the state diagram, and with the help of the excitation table we have created the circuit excitation table, and with the help of the corner map we have obtained the simplified Boolean expression or the equation. So that is all about step 3. Now let us move on to the further step of step 4. First let us try to write all the Boolean expression that was obtained from the previous step, and then we have to start to draw the logic diagram with the help of flip-flops. As it is mentioned in the step 1, we need to draw 3 flip-flops. So let us try to draw 3 flip-flops, JK flip-flops. Okay, this is flip-flop 0, flip-flop 1 and flip-flop 2, and the various inputs are going to be J0 and K0, J1 and K1 and J2 and K2 for the corresponding flip-flops. So after drawing all the flip-flops, we have to just give a clock signal. So the clock signal is given simultaneously to all the flip-flops. So this is the clock signal, clock pulse, CLK, represented as CLK. Now from the simplified Boolean expression, let us try to give the input combinations for all the flip-flops. So the various input combinations for J0 and K0 are 1. So J0 is equal to 1, K0 is equal to 1. So it is a high signal. So let us try to give 1. So let us try to give 1 to J0 and 1 to K0. So we have completed giving the input combinations for the flip-flop 0, that is FF0. Next, let us move on to the second flip-flop, that is FF1, flip-flop 1. For J1, the expression is going to be Q2 bar Q0. So where is Q2 bar? Q2 bar is available here. So we have to make use of a AND gate because Q2 bar and Q0. Also, we can take Q2 bar from the last flip-flop. Therefore, let us try to connect Q2 bar to AND gate, and the other input for the AND gate, it is going to be Q0. And the output of this AND gate is given as an input to J1. So, Q2 is given as an input to AND gate and Q0 is given as an input to AND gate. And the output is given as an input to J1, as that is Q2 bar and Q0. So, we have completed giving the input for J1. Now, similar way we will try to do for K1. So, K1, the simplified expression, it is going to be Q0. Therefore, where is Q0? Q0 is available here. Therefore, directly you can connect Q0 to K1. So, Q0 is connected to K1. So, we have completed giving the input combination for the second flip-flop. Next, in a similar way, we will try to do it for the flip-flop 2. What is the expression obtained here? It is AND of. That is, we have to make use of AND gate. Q1 and Q0. So, this is Q1 and this is Q0. Let us try to give input for the AND gate. That is Q1 and Q0. And the output of this AND gate is given as an input to J2. So, Q1 and Q0 is given as an input to J2. So, we have completed giving the input for J2. In a similar way, let us try to do it for K2. K2, it is going to be Q0. So, you can directly connect Q0 to K2. We are taking it from here. So, we have completed the process of giving the input combinations for this counter design of flip-flops with the help of flip-flops from the Boolean expression that we have obtained from the step. Now, let us try to take the outputs. So, outputs are going to be, so let us create the nodes and let us try to take the outputs Q0 and Q1 and Q2. So, the outputs of this synchronous counter, it is going to be Q0, Q1 and Q2. So, now we have completed the process of designing a synchronous counter. Hope you have understood the process of designing a synchronous counter with the help of the flip-flops. Thank you.